that basically means that things can be at multiple different locations at one time. So I guess there we go. Okay. All right. Let's see if I can change slides before I begin. Okay, I can. Okay. So the theory of everything. So what is that? Well, quite literally, it is the theory of everything. It's why we exist. It's why the universe exists. And yes, it involves quite a bit of math and theoretical physics, but it doesn't have to be as abstruse a concept as most people make it out to be. See, if you're, I think anyone can say that the intricacies of the universe are beautiful. I mean, everyone can agree with that, but no one understands all of it. I mean, especially a 17-year-old barely out of high school. So I'm just going to conduct this talk in the ideology of one of the things that Albert Einstein said. He says that if you can't explain it to a 3-year-old, then you don't really understand it yourself. So I'm going to attempt, in layman's terms, to explain complex concepts of string theory and quantum physics. So here we go, and hold on to your pants, everyone. So, what is quantum physics? So you gotta think the small stuff. Basically, quantum physics is the study of subatomic particles that include forces, mass, and how things interact. So basically, ninth grade physics, if you go here. And oh, well, okay, actually, that's good. So here, the standard model is a compendium of such particles, basically like a periodic table. So as you can see, it's made of quarks, leptons, and bosons, and the Higgs particle, which we'll talk about a little bit later on. But the difference between them is, so each of them have an intrinsic property called spin. And what that is angular momentum. So if you do this, that's angular momentum. This paper was angular momenting, I guess you could say. So quarks have a fractional charge, or angular momentum. Leptons have a negative charge. And gluons, photons, Z and W, bosons are force carriers, which means that they dictate how things we can see in the macro world, or things we can see, interact. All right, now a little bit of history. Some history. So, the ultraviolet catastrophe. So, I mean, obviously, it didn't go well for some people in studying this thing. And so basically, the ultraviolet catastrophe resulted in the discovery of quantum physics as we know it. So, basic physics, that all bodies emit energy in the form of light. And in the 19th century, physicists created the theoretical black body. And just an all black body, pitch black, would absorb all light, and it would be in thermal equilibrium with its environment. And by extension, that means that black bodies would emit light of all frequencies. And that, by extension, means that infinite amounts of UV energy, of ultraviolet energy, which is the highest frequency, it would just be constantly emitting UV radiation, and that is possible. I mean, that's impossible. It's impossible. As we know, it's impossible. Okay. All right. So I'm going to see if I can actually do this. If I can show, because I wanted to show some. So basically, I wanted to show you a video of thermal imaging, which is basically it's a visual representation of bodies emitting UV radiation. It's in the link on the next slide. Sorry. There we go. Okay. So copy.
There you go.
God, this is like. Okay, control, copy. Woohoo! All right, good job, me. All right, it's in there. So it's just I'm just gonna show a quick little clip. Ignore the commercial, and it's
Where's the volume?
being a pain because I can't skip it right now. Oh boy.
Oh yeah.
Sorry, guys.
There's a reality in which I would have tested the sound quality before the presentation, but unfortunately, I don't have the privilege of being in that one. So, sorry, guys. But it's a cool video. It's a cool video. It's alright if you don't have sound. Yeah, if we don't have, just for the sake of time. Okay, well, if we have time at the end, yeah, put it up. So I think that, okay, we can get this working.
There you go.
Oh, there we go! Oh my god, okay, yeah, so this is a lady playing badminton, and she is emitting UV radiation. I'm just gonna let you watch this 1 minute and 2 second video. Actually, probably shorter than that, but yeah. And UV light reflects heat, which is why she's getting increasingly more yellowish white. So yeah, I think you've got the right idea. Right idea. All right. Cool.
Maximize it. Present. There you go.
All right. So that's over. Okay. So Max Planck, he's a German physicist, and to solve the ultraviolet catastrophe, he posited that energy is emitted in small bits called quanta, the size of which is given by Planck's equation. Now, if you ask me, I don't know what any of this means, but I know that it corresponds to the size of any given quanta. So because energy is emitted in small pockets of energy, you can see that there is an energy threshold right after visible light, which means that quanta are released in low energy packets, which means that it can't an infinite amount of energy can't be released at once. Sorry about that. Okay, good God. All right. So quantum field theory. So quantum field theory explains how subatomic particles interact with forces which are known as fields. So what are fields? Fields are light, electricity, and gravity and mass. Gravity and mass are a bit special. They're searching for a particle that is the force carrier of gravity, known as the graviton. They haven't found it yet, but they have found a particle known as the Higgs boson particle. Oops. Yeah, the Higgs boson particle, which is also called the God particle. And can anyone guess why it's called the God particle?
So.
You can't see it?
Okay, well, I'm not sure if I already explained this, but the Higgs boson particle, it dictates mass. So it's literally the reason why we exist. And that is why it's called the God particle. So if you wanted to reconcile your religion with science, then there you go. And so I'm not sure if I'm going to try another video. I might just wait till the end. But I wanted to show you the magnetic field in action. I'll just wait till the end, though.
Uh-oh.
Jesus Christ. I'm going to validate where everything's constantly next to it. There we go. All right. Yeah. So everyone look at this image.
Okay.
This image is the Higgs boson particle as represented by the Large Hadron Collider. And a Large Hadron Collider is a particle accelerator. And what a particle accelerator does is it shoots little tiny bits of gold atoms at each other, and they hit each other, and they see what happens. So yeah, that's basically the life of a physicist. Just blowing stuff up occasionally and seeing what happens. Yeah, this is very touching. All right, so on to general relativity. So unlike quantum physics, general relativity deals with the macro world, or the big stuff. And it's a concept created by Einstein, which combines both space and time into one field or force, which is gravity. And so Einstein came up with the cosmological constant. And basically the story behind this is that, and the cosmological constant is basically a vehicle for explaining how the universe expands. So Einstein and his buddies were meeting in Berlin, him, Friedman, and Lemaitre, and they were discussing, is the universe static or not? And Einstein was like, I don't think so, guys. And his buddies were like, are you sure about that? He was like, you know what? Just to be careful, I'm going to add in this cosmological constant. So this cosmological constant, basically, it accounts for the expansion of the universe. And it's represented as lambda in the Friedman equation. So that is why the universe is expanding. And evidence of the universe's expansion can be seen in the Doppler effect, which is basically, I want to show you another video, but okay, so basically just imagine there's a car, okay? In the car, it's coming and then it's going. And it goes like, and that is the Doppler effect. When things are farther away, they get redshifted. And when things are closer, they get blue-shifted. And the Doppler effect is how they know that things in the sky are getting farther and farther away. Fact. So, general relativity and quantum physics are mutually incompatible because of quantum superposition, which is what I was talking about earlier. And in layman's term, I guess you could say quantum superposition it's like quantum jitters. So it's like if something was here 1 second and here another, or here 1 second and here at the same second at the same time. So basically, everything is in quantum superposition until it's directly observed. And according to quantum physics, with general relativity, everything has a relatively fixed position, it makes sense that general relativity, with everything being in a fixed position, and quantum physics, with everything being all over the place at once, would be mutually incompatible. So how could we unify the two? Well, I got an answer for you. String theory. Oh, yeah, string theory. So string theory suggests that the universe is made of one-dimensional little noodles or strings, and that the geometry of these strings dictates force, reactions, etc. And it also suggests that we are living in multiple dimensions. So these theoretical dimensions are represented by Calabi-Yau manifolds. And Calabi-Yau manifolds are these things right here. And these little folds represent multiple universes undulating all over each other. It's all over each other. And scientists have found many different shapes of these Calabi-Yau manifolds and are still looking for the one that describes our universe today. And so I guess the lingering question you could have is, what happens when they find the one? What happens when they find the right shape? Well, that is where you get, sorry, I was going to show a video. That's where you get the theory of everything. That's where you get the theory of everything.
Oh my gosh.
So, the theory of everything, like I said at the beginning, explains life as we know it, down to the smallest intricacies. And it's just so profound that Einstein was on his deathbed. He was on his deathbed trying to create the equation to find a theory that would unify general relativity and quantum physics. And with the theory of everything, we can't know what would happen 10 to the negative 43rd seconds before the Big Bang, which is inconceivable to me because I can't even pronounce it. So the theory of everything is just really profound, and it's literally why everything the way it is, why everything is the way it is. I just you just have to sit on it, you know. I can't really explain it any further. But I know who can.
Oh no, there's more.
So Michio Kaku is a physicist who's a lot wiser and smarter than I am, and he can properly explain the profundity of the theory of everything. So I'm gonna give this one a go since it's the last video. I don't know if you guys give me your emails, maybe I can email you guys the rest. All right. All right.
A 3-minute video? Come on,
All right, this one's gonna work, guys. Just wait a couple seconds. You can watch this video too, if I didn't do a good enough job. Oh my god, okay, there we go. Let's get the audio.
Theory of everything, the crowning achievement of modern science, ever since humans first began to ask, what is the world made of? Are we going to have wonders, technological wonders? Am I going to get better color television? Am I going to get better cable reception? Am I going to get a better internet? Well, the short-term answer is no. It's not going to affect your life or the life of anyone directly. But look at it this way. This theory of everything is also a theory of space and time and the universe itself. It will answer some of the deepest philosophical, theological questions of all time. What happened before Genesis, chapter 1, verse 1? What happens if time can be bent into a pretzel? What happens if space has holes in it? What happens if you could somehow manipulate space and time itself? These questions are far beyond the theories of Einstein. Einstein's theory breaks down at the instant of the Big Bang, where it's useless. Einstein's theory breaks down at the center of a black hole. What lies on the other side of a black hole? What lies on the other side of a Big Bang? Einstein's theory are useless because they simply blow up at that point. This is where a theory of everything comes in. String theory, being a theory of everything, actually allows us to go before the Big Bang, where there might have been a multiverse of universes. With our universe being a bubble, we live on the skin of the bubble. The bubble is expanding, and there are other bubbles out there floating in 11-dimensional hyperspace. And these bubbles, in turn, are connected perhaps by gateways, by tubes. These are called wormholes. And we physicists take them very seriously. These wormholes may or may not be stable, we're not sure, but they are definitely part of the equations of the theory of everything. Now, another thing. Think of human history as seen by a physicist in terms of forces. When Isaac Newton worked out the first force, gravity, that gave us the mechanics. That mechanics gave us steam engines, locomotives, skyscrapers. The Industrial Revolution was in part spurred on by the mastery of the first force, gravity. The second force is the electromagnetic force, the force that lights up our cities, laser beams, computers, all the electronic wonders that we see around us is a byproduct of the second force. So when physicists worked out the second force, that unleashed the electric and the computer revolution. And then the weak and strong nuclear forces were worked out in the last century. That gave us nuclear power. That gave us the energy of the stars.